Welcome to this lesson on MEMS success stories. Before we go into detail of the various micro nanofabrication methods, let's have a quick look what MEMS are and how we are actually using them day by day. We have invited for this lesson a guest lecturer who is a real expert in the field. So let me introduce Dr. Julien Acamone. He is responsible for the industrial partnerships and business development in MEMS within the Silicon Components division of CA Leti in Grenoble, France, one of the largest MEMS R&D centers and foundries. Julien will show you some selected MEMS examples. He will in particular highlight how microfabrication has enabled such systems to become so performing and cost efficient to manufacture. So Julien, the floor is yours.
Thank you, Jürgen, for the introduction. Hello, it's my honor and pleasure to give this lesson on successful MEMS products. Let's start right away. So maybe not everyone has noticed yet, but MEMS have become ubiquitous in our daily life. One example is a multiplicity of MEMS devices inside smartphones. This scheme depicts a teardown view of the iPhone 6 and the various MEMS devices present inside it. In this lesson, I like to focus on three applications. First, accelerometers, so acceleration sensors. Second, microphones. Third, BAW resonators and filters. BAW stands for bulk acoustic wave resonators. Let's start with the accelerometers. Technically speaking, the most classical device is a capacitive comb drive accelerometer with electrostatic actuation and capacitive detection by means of a set of lateral combs. The physical principle is rather simple. This sensor detects a capacitance variation induced by an acceleration. Let's illustrate how this device works. This scheme depicts a top view of a proof mass, which is sensitive to accelerations along the x-axis. This proof mass acts as an inertial mass. It can move laterally and is anchored in 4 points. In this picture, the movable suspended parts are in gray. The anchored or fixed ones are in black. Typically, a proof mass is between 100 and 200 microns wide and long. This proof mass is equipped with a set of lateral comb fingers. They all have an opposite and mechanically fixed comb finger. The fact of using combs provides a larger capacitive area, which turns into an enhanced capacitive readout. Let's zoom on a few fingers. In this example, 4 capacitors are depicted, all with a capacitance C and a gap G. The 2 ones on the left are polarized at plus V in. The 2 others at minus V in. Let's suppose, for example, an acceleration towards the right side. It induces a counterforce towards the left, which makes the proof mass and its combs move towards the left too. So let's show it again. Consequently, as their gap narrows, the capacitance of the 2 left capacitors becomes C plus delta C. The capacitance of the 2 right ones becomes C minus delta C as their gap widens. Overall, this provides a differential readout, and the output voltage is approximately equal to delta C over C. The key parameter in terms of sensitivity and resolution, also named limit of detection, is a gap G, which must be minimized as much as possible. It is generally in the range of 1 micron. This video is recorded inside a scanning electron microscope. So the images here are recorded with an increasing zoom. Here you can see the polysilicon structures with the moving parts, in particular the combs moving in front of the reference electrodes. So the motion is the combination of the electrostatic attraction and the restoring force of the springs. Basically, here the motion is in the range of a few microns laterally. This is just an example of layout, but of course, many designs are possible to make the same function. Let's take an example of fabrication process of such capacitive accelerometers. This scheme depicts a cross-sectional view at the end of the process. The MEMS layer can be either a monocrystalline silicon layer if an SOI substrate is used, or a polycrystalline silicon layer, also named polysilicon. The routing of the mechanical structures is made with partially suspended polysilicon interconnects. The mechanical structures are released by removing the underlying silicon oxide sacrificial layer by wet or vapor HF etching. HF stands for hydrofluoric acid. The MEMS active parts are encapsulated by a polysilicon thin film packaging, which provides a hermetic cavity at ambient pressure, protecting the MEMS from moisture, humidity, and dust. The input and output signals are brought and picked up through metal pads, here for example, or here. Let's also mention that some silicon structures are on top of silicon nitride pillars in order to electrically isolate them from the substrate. One of the key steps is the deep reactive ion etching, abbreviated as DRIE, of the silicon MEMS layer. This etching has to provide vertical and smooth sidewalls with a high aspect ratio of at least 20. The thicker is the silicon MEMS layer, the wider is the gap due to the maximum affordable aspect ratio. Typically, the silicon MEMS layer is around 20 micron thick and the gap is about 1 micron wide. Let's zoom on a particular area. This scanning electron microscope, abbreviated as SEM, image depicts a set of movable and fixed comb fingers. They feature all the necessary characteristics I mentioned. They have vertical and smooth sidewalls and small gaps. So let's talk about application now. First, which MEMS companies sell this kind of devices? Let's cite Bosch, ST Microelectronics, InvenSense, Analog Devices, etc. As I mentioned before, accelerometers are present inside smartphones, in particular for screen rotation and for gaming. I like to mention another use case. Inertial MEMS are also widely used in automotive for various purposes. Let's take the example of NXP's HAR-MEMS technology. Such accelerometers are implemented to detect front or side crash in order to trigger airbags. In the left picture, the car contains 5 so-called accelerometer satellites or modules. At the center of the car, an airbag electronic control unit, ECU, also senses crashes and triggers airbags. Let's move to example 2, microphones in smartphones. Generally, what is called a MEMS microphone is a dual die component. The MEMS microphone itself, most of them are based on capacitive detection, and its ASIC readout circuit. ASIC, as you may know, stands for Application-Specific Integrated Circuit. They are connected one to each other by wire bonding. MEMS and ASIC dies are both housed inside a package which has a sound port either on the top side or at the bottom of the package. This scheme depicts a bottom port component. The package has multiple functions. Of course, as in all MEMS, it protects the device and provides a crucial electromagnetic shielding. In addition to that, the back chamber plays a very important role on the acoustic performance. The larger it is, the higher the signal-to-noise ratio, abbreviated as SNR. Although piezoelectric microphones are emerging, Capacitive ones are by far the most widely used. How do they work? Basically, there are two suspended parts, a movable membrane, here in red, and a fixed backplate, here in purple. Both form a variable capacitor which senses the motion of the movable membrane caused by any incoming sound wave. In this example, the sound comes from the bottom and the package is not depicted. To repeat again, the sound wave generates a pressure differential between the front and back chamber. Consequently, the membrane is deformed, and this results in a capacitance variation. The membrane contains ventilation holes, not depicted here, to allow the compressed air of the back chamber to flow out. The backplate contains perforation holes, basically to transmit the sound to the back chamber. The membrane diameter is typically in the order of 1 mm. Regarding the microphone bandwidth, it has to cover the human ear bandwidth, so from 20 Hz up to 20 kHz. Let's turn to the fabrication process of such sensors. This example is quite representative of all capacitive MEMS microphones. Generally, the process is a mix of surface and bulk micromachining. The first critical process module is the deposition of the low-stress polysilicon membrane on top of an SiO2 layer. The second critical process module is the successive deposition of a thick polysilicon layer and of a highly tensile silicon nitride layer. These two layers form the backplate, which must be rigid enough to constitute a fixed reference electrode. Finally, metal interconnects are deposited and patterned. Another important step consists in realizing a deep cavity from the backside. It's obtained either by wet etch, for instance with KOH, or deep RIE. The first option is cheaper, but sidewalls are inclined. The second one, with deep reactive ion etching, represented here, is more expensive, but sidewalls are vertical, what provides a larger cavity. The final critical step is a membrane release by removal of sacrificial SiO2 layer by wet or vapor etch. Anti-stiction control is crucial during this step. So let's talk about application now. First, which MEMS companies sell this kind of devices? Let's cite Knowles, Infineon, Omron, STMicro, InvenSense, etc. As I mentioned before, microphones are present inside smartphones. The image below illustrates the number of MEMS microphones inside the iPhone as a function of its generation. Nowadays, the iPhone 6 contains 4 microphones. Some are used to pick up the voice, others for the cancellation of surrounding parasitic noise, and the last main function is for the hands-free kit. Let's move to example 3, BAW resonators in smartphones. As I said, BAW stands for bulk acoustic wave resonators. The resonance frequency is generally in the range of the gigahertz. In terms of structure, BAW use a piezoelectric layer made of aluminum nitride most of the time, sandwiched between a bottom and a top electrode, usually made of molybdenum. In terms of resonance mode, a thickness mode, either with longitudinal or shear vibration, is operated. In the longitudinal mode, the resonator expands and contracts all the time in the direction of its thickness. Its resonance frequency is half the velocity of sound divided by the resonator thickness. The velocity of sound is the square root of the Young modulus divided by the density. With a thickness of 1 micron approximately, the resonance is around 5 GHz. BAW resonators are used to implement bandpass filters. I'll get back to this in the next slide. In this sense, the so-called KT-square coupling coefficient is critical in terms of filter bandwidth and insertion loss. The KT-square is given by the ratio between the difference between the resonance frequency and the anti-resonance frequency divided by the resonance frequency. In fact, the kT square depends on piezoelectric material properties. Therefore, the deposition and further process of the piezoelectric layer is crucial. How can we build a filter using BAW resonators? Basically by implementing a ladder filter architecture. Each unit cell that can be replicated n times contains two BAW resonators, a series one and a shunt one connected to ground. Let's explain how it works by observing the filter response. At the center of the slide, the frequency response of the shunt resonator is depicted at the top. The one of the series resonator is depicted here, and this is the response of the whole filter. Please note that the shunt resonator response is shifting down to lower frequencies such that the shunt anti-resonance coincides with the series resonance. In state A, both resonators are far from their resonance frequency. Therefore, they both behave as capacitors. In state B, the series resonator is still far from resonance, and it behaves as a capacitor, while the shunt one is at resonance. In other words, its impedance is minimum. In fact, in this state, its impedance is equal to its so-called motional resistance, which is less than 1 ohm. As a consequence, the output node is almost grounded and there is no signal transmission. In state C, the series resonator is at resonance. In other words, its impedance is minimum and of less than 1 ohm. In the meantime, the shunt one is at its anti-resonance. In other words, it's at its maximum impedance and it behaves as an open circuit. As a consequence, the impedance between input and output nodes is minimum and the signal transmission is maximum. In state D, the series resonator is at its anti-resonance, in other words, at its maximum impedance, and it behaves as an open circuit. The shunt one is far from resonance and behaves as a capacitor. As a consequence, the impedance between input and output nodes is maximum and the signal transmission is minimum. In state E, the situation is very similar to state A. Both resonators behave as capacitors. So this is basically a summary of how a ladder filter using BAW resonators works. Let's turn to the fabrication process of BAW. Let's first mention that there are two types of BAW due to the fact that there are two main approaches of acoustic wave confinement. So-called F-bar thin film buck acoustic wave resonators are suspended resonators over an air gap. So-called SMR solidly mounted resonators consist in unreleased resonators, so I mean not suspended, located over a Bragg mirror that reflects back the waves. We'll focus on this type. This is a cross-sectional view of an SMR processed on a high resistivity silicon substrate. You can see the Bragg mirrors here, which are made of tungsten plates surrounded by SiO2. The first critical process module consists in depositing an aluminum nitride layer by physical vapor deposition on top of a properly oriented molybdenum bottom electrode. This puttering technique allows obtaining first a precise and uniform thickness. Have in mind that the resonance frequency is inversely proportional to the thickness, and second, good piezoelectric properties which result in high kT square. The top electrode is also made of molybdenum. Another important step is the mass loading of shunt resonators. In fact, shunt and series resonators are identical by design. Then, this mass deposition on top of the shunt resonators allows adequately decreasing the resonance frequency so that the anti-resonance coincides with the series resonator resonance, as I explained in the previous slide. The second critical process step is wafer scale ion beam trimming. By locally removing some material, the ion beam allows precisely adjusting the resonance frequencies of each series and shunt resonators. It's indeed very important that each filter has the same bandwidth and center frequency. The resonators have a silicon nitride passivation in green and are capped with a thin film packaging in pink to provide them with a hermetic and clean cavity at ambient pressure. This optical microscope image shows the top view of a filter chip at the end of the fabrication process. Basically, the white squares and rectangles are metallic contact pads, and the colored squares are BAW resonators which have a typical 150 by 150 square micron area. Depending on whether they are mass loaded or not, I mean series or shunt, the resonator's color is different. So let's talk about application now. First, which MEMS companies sell this kind of devices? Let's cite Avago, that produces F-bars, and Qorvo and TDK EPCOS, that produce SMRs. BAW bandpass filters have become a key element of RF front-end modules of smartphones. Such modules are essentially the RF stage located between the antenna and the analog-digital converter. In this context, BAW filters are used to select a given telecom band. In green, you can see all the filters present in this example of front-end module. And for example, the iPhone 6s contains more than 20 BAW filters dies, either for 4G or LTE connection, or for Wi-Fi connection. I'd like to wrap up this lesson. We've analyzed 3 examples of commercially successful MEMS devices. All these devices have been sold by hundreds of million units, and all of them rely on advanced micro and nanofabrication techniques that you will see in the upcoming lessons of this MOOC. Thanks for your attention.